One more time.
All right, so for the last 3 weeks here, we're going to be focusing on trees and tree-based data structures as our final module. We're going to be developing a data structure that basically provides everything that we want, most of what we want, because we like structures. A structure is something that can be exploited for efficient operations or efficient algorithms. And again, the motivation here is that we want a general purpose data structure to support basic CRUD. Create, retrieve, update, and destroy. And just like a database, right? We want something to hold stuff, but we want it to be efficient, right? Just make sure. Yeah, there we go. All right, we're on. So if you have any questions, go ahead and post to the live stream. But otherwise, we want to be able to put stuff in, retrieve stuff, take stuff out, and delete stuff from our data structure. And we want them all to be efficient. And we haven't quite gotten there yet, right? We've looked at linked lists. And they offered efficient, in other words, order one, constant time insertion or deletion at the head, right? Why? Because that's what you kept track of. It was right there. All you need to do is create a brand new node and make that new node point to this one. It was a constant number of operations. And now that we've got big O analysis, we've got the proper terminology to refer to that, that it's a constant time algorithm. Unfortunately, it was inefficient when we tried to do arbitrary insertions, arbitrary index-based operations were going to be order n. Right? Why? Because you had to start at the head and you had to traverse to that arbitrary location that you wanted, say that it was in the middle, and there were 1 million elements. You had to do 500,000 operations just to get to the element that you wanted to manipulate. Or arbitrary, I should spell that correctly. And then operations. Right, there we go. And then you have array-based lists, right, which are efficient index-based find operations. Right, this is going to be order 1. Why? Because of random access. If you have the memory address where it begins, you know exactly which one you want to go to. You know how many bytes each one of those things takes. It's just a simple computation. Multiply and add. And then you can jump to that memory location and you're there. Right? It's just a constant number of operations. But insertion or deletion from the start, right? The same head operations that you have with linked lists are going to be order n. Why? Because you need to shift stuff down. If you've got 1 million elements, you need to shift all 1 million of them in order to make space for it. If you want to delete that element, you need to shift 1 million elements down in order to not have gaps. Right? We also looked at stacks and queues. Right? Stacks, queues. Right? They offered efficient operation. All the operations were efficient, right? The push, pop, or NQ, DQ, right? But they were still limited. They were limited access, can't spell today, sorry. Limited access data structures. They were not general purpose data structures where we could put anything in what we wanted, retrieve anything we wanted, delete anything that we wanted. You could only work at one end. And by making that restriction, that's what gave us these efficient operations, by limiting your access to those data structures. And of course, if you've got an array and you've got additional structure like being sorted, right, an array-based list, and it's sorted, then you can exploit that using binary search to have order log n operations. Okay? Our ultimate goal is to find a data structure that offers all of these things efficiently, order log n. Okay? And the one that we're going to focus on for the rest of the semester here are trees. Trees offer the potential for order log n operations. We're not going to get there fully. I will show you what it takes, what additional steps it takes to get there to what are called balanced binary search trees. But today we're just going to justify why what are trees, why should we be looking at them, and why do they offer the potential for efficient operations. Have you already covered graphs and graph theory in 235? Yes, I'm seeing no. 235H, yes? No, okay. All right, that's fine. A graph is a collection of nodes or vertices along with edges that connect to it. Now, in graph theory, you would call these things vertices because that's what they are. But over here in computer science, we're going to call them nodes because they store data. Right? We don't just want arbitrary nodes, right? Ultimately, we're going to use have a purpose for these, and we're going to be storing stuff in them. And so consequently, we call them nodes. Here's a nice little graph over here. If you were coming from like discrete math and graph theory, you would call this G equals V comma E. Right? V is the vertex set. A, B, C, dot, dot, dot. How many do we have? E, F, G. There we go. Right? And so therefore, the cardinality of the vertex set here is 7. We use the variable n to denote the size of the vertex set. The edge set here is a series of unordered vertices, or pairs, I should say. A and D, right? That's connected. How? A and D right there. But is BC in this? Or is it? No, BC. Is that a pair? Like, is there is there an edge from B over here to C? I don't see one, so no. Right. So, what else? Give me another edge that's in this. BE. What about GE? There we go. Yes, that is a pair, right? It's right here. G is connected to E. We don't generally write it like that, though. Why? Because E, G, that's in lexicographic order. That's the exact same thing as GE. Right? This is an unoriented graph. This is an undirected graph. You can have directed graphs, in which case there are arrows as your edges instead, in which case this would not be equal, but these are undirected graphs. Dot, dot, dot. Right. Now, what is the size of the edge set in this case? Here we use the variable m, and if you go through and count all these up, like I did right before class, is 13, because in the last class I messed up and I overcounted, and I thought that there were 13. I thought there were 14, but I'm pretty sure now that there are 13. Go ahead and stare at that for a while and tell me if you see otherwise. All right? But otherwise, that's the vertex set, that's the edge set. It's unoriented, it's undirected, and edges connect vertices. Now, does it matter that, say, this edge and this edge right here, they intersect? No, that's just how you had to draw it. You could have drawn A to F over here like this. If you can draw a graph without any intersections of edges, that's called a planar graph. Not all graphs are planar like that, right? All right. So, some more terminology here. What about a tree? A tree is an acyclic graph, a graph without any cycles. To understand that, we need a little bit more definitions. A path in a graph is a sequence of edges, of vertices, each connected by an edge. A cycle in a graph is a path that begins, ends at the same vertex. Okay, so let's come over here, and you tell me, what are some paths here? I could go from, say, A to D to G to B, right? There is a sequence of connected vertices. Why? A to D, D to G, and then G over to B. What is the length of that path? The length is defined as the number of edges on that path. In this case, it's 3, because I went 1, 2, 3. Right? How many vertices are on that path? 4, right? Just like your fingers. If you've got 4 fingers, how many gaps are between the fingers? However many fingers you had minus 1. Right? So the length of this path is 3. What about this path? A to D to G, back to D, over to F. Right? So let's visualize that. A to D to G, then back over to D, and then over to F. That is a path, but it's not a simple path, because I traversed this edge twice. Okay? We're not going to consider those. Those are not under consideration. You can go ahead and talk about those, non-simple paths, non-simple cycles, but we're not going to. We're going to keep it simple. Okay? What about A to E to G to C to D to A? There we go. So let's follow that. It was really complicated. I shouldn't have made it that complicated, but A to E, E to G, G to C, C to D, and then over to A. I ended up at the exact same spot that I began. And by the way, because it's not oriented, it's undirected, this is the same path as B, G, D, A. Same length, it's just you're going in reverse. Likewise, this is an unoriented cycle. Where does it start? Where's the start of a circle? Here, let's draw a perfect circle. There we go. There's a perfect, I can draw perfect circles. Right. Where's the start? Be a smart mathematician. Where's the start? Right there, yeah. At what? What is it? Pi, pi, right? Radius 1, 0. If it's a unit radius, so that you have radian 0 is what I want to look for, right? At degree 0 here. Right? That's the smart answer. But really, what's the real answer? A loop has no start. You can start at an arbitrary location and come back to where you started. So there's no start here, even though I drew it as A. This is a cycle. What is the length of a cycle? Be careful here. 1, 2, 3, 4, 5. In this case, the length is 5. How many unique vertices did we have? 1, 2, 3, 4, 5, and then you went back to A, right? Through this edge right here. So for a cycle, the number of edges on it is equal to the number of vertices on it is equal to the length. But for a path that's not a cycle, it's different. It's -1. Okay? All right. So the length of a cycle or path is the number of edges along it. We only consider simple paths cycles that don't repeat an edge or vertex. Okay? A tree then is a graph with no cycles. So we already found a cycle over here. Is it a tree? Nope. Let's go ahead and take away a few vertices and make it a tree. So where right there. There we go. There's the same orientation of vertices, but now it's a tree. Verify that by looking at any of the edges, and can you ever form a cycle? No. Right? Now be careful. You can disconnect it. So let me go ahead and disconnect this right here, and maybe this right here. There. Right. That's not a tree anymore. It's a collection of trees. This is a tree, this is a tree, and this is a tree. What do you call it when you've got many trees? A forest. So this is a forest. Right? What do you call it when you've got a tree of size 1? Nebraska? We've got a lot of trees. We've got too many trees. We've got too many crappy Dutch elms with Dutch elms disease that need to be cut down. We need natural trees, trees that are native to Nebraska. I'm not an arborist, though, so I don't know what's native. I just know that the trees in my neighborhood are extremely ugly and invasive. And the white ones, I forget what they're called. They're blooming right now, and they stink. Right? What are they called? Does anybody know? Anybody an arborist? Right. They're gross and disgusting. And they're not even pollinators. They are an invasive non-native tree. They need to be gotten rid of. Anyway, where do you start? With a seed. Right? So somebody suggested one year that we call a single node tree a seed. Why? Because it's eventually going to grow. Right? All right, so we're not going to be considering forests. Okay? All right. Well, remember that we had 7 vertices before. Now you tell me, how many edges do we have? This should be much easier to count now. 1, 2, 3, 4, 5, 6. What's the relationship there? N minus 1. That's always going to be the case for a connected tree. Look at an example. If we have 4 vertices here and 3 edges, can we add one more edge? What if we did? What would we necessarily have? We would induce or create a cycle. What if we had one fewer edge? Then we would have a forest. Right? So our first observation here is that for our connected trees, we're going to have a very, very close relationship. So let's make some observations. Observations. For a connected tree with n nodes, there will be n minus 1 edges. Right? What else can you observe about this tree that's hanging over here? What about the paths? What if I went from A to, I don't know, G? Is there a path, first of all? It's connected, so there has to be at least one path. Okay? What does that path look like? A to F to C to G. Right? Can there be another path? Could there be another path from A to G using some other vertices or something? What if there were? Then I can go from here to here and then traverse the original path, end up back where I started. What is that called? A cycle. Right. So my second observation is that between any 2 nodes, there is exactly one unique path. Right? Otherwise, it would be disconnected, and there's 0 paths, or there would be 2 paths, and you would induce a cycle. Right? This is a lot of structure already. How can we exploit this structure? Right? Well, to do that, the first thing I want to do is add some convenient conventions or orientation. Right? So now what I want you to do is imagine that you could take this out of the screen, pluck it up by any one of these nodes, and hold it out in 3 dimensions, and then dangle it. Dangle it so that everything, gravity takes over and all of these nodes fall down. Suppose that I did that off of A. I would have A up here at the top where I'm holding it. Gravity takes over, and all of its children, D, E, and F, are hanging off of it. D, E, and F. Okay? Now I've got some additional nodes here. Hanging off of F is C. Hanging off of C is G. And hanging off of G is B. Okay? That's one possible orientation. Right? Now we've got top to bottom. Not only do we have top to bottom, but we have left to right. Right? So this is the top of the tree. This is the bottom of the tree. This allows me to use some terminology. Up here, the one at the very top is going to be a unique root. These are going to be leaves. Right? And this is also a leaf. My first observation is that our trees are growing the wrong way. They're growing downward, right? A real tree that's outside is going to have roots at the bottom, and then it's going to grow up and have leaves at the top, right? That's not the way that our trees grow. And why? Because 150 years ago, when Cayley introduced them, the very first paper about them, he grew them top to bottom, left to right. And the reason for that is it's going to eventually hold data, not just A, B, C, D, E, F, G, right? It's going to hold some data that we're going to be reading. And in English, we read top to bottom, left to right. And so it's going to be much easier to think of these things and visualize them if our trees are growing downward. That's not the only tree that grows downward, though, right? What other trees have grown downward in this class? Inheritance diagrams. UML diagrams. What are UML diagrams? They're graphs, right? And hopefully they're trees. They don't have to be trees. You can have multiple inheritance, in which case they're mangroves, lattices, things like that. Java doesn't allow that. Awesome. They're still trees in Java. But if you went to C++, where you've got multiple inheritance, then you've got like general graphs. Graphs are used all over the place. They're used in almost every single STEM discipline. Is anybody taking chemistry? Or I was not able to give the correct diagram for H2O. I've got two H's and an O. Is this it? Does anybody take chemistry? Or it goes O and then H, like this? H2O? Is one of them like a... Oh, I don't know how to do that. Anyway, you've got covalent bonds, and what other kind of bonds? Okay, so like this, what's the difference? Do you know? Oh, okay. I don't even know enough to know that there's not a difference there, but they're both covalent. All right, so anyway, every discipline will have some sort of a graph representation. Why? What are graphs? Things and relationships between things. It doesn't get any more general than that. In fact, if you're taking 235 right now, you probably started out with relations. What are relations? They're a subset of X, Y pairs, a binary relationship, right? Such that some relation here holds. Say that X is less than or equal to Y. And then our universe of discourse here is all integers or something. And so that 3 and 4 are related, but 4 and 3 are not related. Right? That's in the relation, but that one's not. Right? So it's not symmetric. Right? Is it transitive? Yeah. Why? X is less than or equal to Y, less than or equal to Z. Does that hold? Yep. Right. Is it reflexive? Is X related to X for all X? Yeah, because X is less than or equal to X. Well, what is this thing right here? It's just a bunch of X's and Y's, and they're either related or they're not. Right? A relation, it doesn't get any more general than that. This is why a relation is a graph. Right? And depending on the type of relation, transitive, reflexive, irreflexive, not transitive, etc. If you've got these properties, then you get different types of graphs. Okay. Symmetric graphs are undirected graphs because you can go from A to B and back. If it were directed and you don't necessarily have the inverse relationship there, then it's not symmetric. Right? That doesn't mean that it's anti-symmetric. Right? Don't get those confused. Anyway, that's your little digression of why graphs are useful. Okay. So our orientation is going to be, we'll orient graphs top to bottom, left to right. Right. This, at the top, we have the root. Right. It induces a parent-child relationship. Right. And there it comes the other application of trees. Right. Where have you seen trees that grow downward in real life outside of STEM disciplines entirely? A family tree. Right. Where would you put yourself? Down here at the bottom. When you have kids, if you have kids, they're going to be below you. Your ancestors are up, your descendants are down, right? So you can talk about ancestors, descendants, right? You can talk about grandparents, great-grandparents. You can talk about children, great-grandchildren, etc., right? So all this familial, family relations, you can use those terms with respect to our trees as well, okay? A node with no children is a leaf node. Right. Excellent. Did I already erase it? No, I did not erase it. Great. So that's only one orientation. What's another orientation that I could have done? For this one, I'm going to, let's see. I'm going to go ahead and grab C. There you go. So once again, take this thought experiment of me grabbing C, pulling it out, and then letting gravity take over and everything dangling off of it. I've got F and G. Right. Off of G, I've got B. Off of F, I've got A. And off of A, I've got D and E. By the way, I could have written it as ED. Why didn't I? Well, D comes before E. If we're going to orient this top to bottom, left to right, I'm also going to take advantage of lexicographic ordering. Okay? Now, observe here. Over here, the root had 3 children. F had 1 child. C and G both had 1 child. And then B here has no children whatsoever. Over here, we have even more structure. Everything either has 2 children, 1 child, or no children. That's what's known as a binary tree. A binary tree where you restrict it further such that there's only exactly, at most 2 children, that's a binary tree, okay? So, binary trees. There we go. A tree that has at most 2 children per node is a binary tree. It can have, each node, I should say, each node can have 1 child, 2 children, or no children. And we can also orient the children, right? We can orient the child nodes so that there is a left child and a right child. Now, I didn't draw it that way initially. What I did was I immediately put, let's see, F right below it here. But now I am going to orient it so that it's a left child. And to do that, I'm simply going to just take this subtree over here, move it a little bit, and make it a left child. There is no right child, okay? I won't even draw that. Now what about B here? I'm going to move that as well. I'm going to move it so that it is a right child. There we go. And now I've got something that's looking more like a binary tree, right? Because I know that this is the left, the way that I've drawn this, I know that A is the left child. I know that there's no right child. Right? There are no left, no right, no left, no right, right? But there is also no left here, and then there's a B with left. And then, of course, C has both children, A has both children, D and E, left and right, respectively. Okay? All right. If a node has no parent, guess what? It's the root, now that we've got this terminology. If a node has no children, it is a leaf. Right? Now, we can define depth. The depth of a node, U, is the length of the unique path from the root to you. The depth of a tree is the maximal depth of any node. So now we're going to look at another example here in a moment. But remember, I want to recall that there is a unique path. Why? Because it is connected and it is a tree. There's exactly one path and one path only from the root to any other node. Right? That's the structure that we're exploiting here. Right? So that if you want to explore this tree and you start at the root and you need to get to a node that contains data, there's only one way to do it. Right? That's really going to help us out on to develop our algorithms and to make them efficient. Let's take a look at a much larger example here of a binary tree. There we go. There it is. So let's look at the depth of these things. Let's look at B. What's its depth? 1. Why? What's the length of the path from A, the root here, to B? It's 1. So depth and nodes. There we go. Well, C, because I drew it on the exact same level here, you can probably guess that it's also going to have depth 1. Everything at the next depth, D, E, F, it all has depth 2. G, H, I, J, K, all have depth 3. L, M, N, O, P, Q, and R. Not R, but those have depth 4. What about depth R of R? 1, 2, 3, 4, 5. It has depth 5. So what is the depth of the tree if this is T? Depth of T. It's the maximal depth of any of these nodes. Therefore, it is 5. If we were to get rid of that node, by the way, we would end up changing the depth of the tree. Right? If I were to erase this, what is the depth of the tree now? 4. Right? If I were to erase one of these nodes, does that change the depth of the tree? No, it's still 4 because it is the maximal depth of any node. Okay? Let's reverse all that. There we go. I left a little bit of space at the top. Why? What is the depth of A? What is the length of the path, the unique path, going from A right back to it? Well, why would you go anywhere? If you want to stay home, do you go out of the door and then go somewhere and come back? No, you stay where you are. Therefore, the depth is, how far did you have to travel? 0. Right? By convention, the depth of the root is 0. Right? So the depth of the root is 0 by convention. Okay? So how can we exploit the structure that we've built up so far? Generally, we will store data in these nodes. For now, I'm going to store integers or letters or something like that. But ultimately, you could store invoices, you could store people, you could store items, you could store whatever you wanted, right? Operations will always start at the root, right? In other words, if you want to search, if you want to insert, if you want to delete, right? And will require traversing from the root to descendant nodes, right? So how can we make this efficient? If, and that is a big if here, if we can make all operations proportional to the depth, they may be efficient. Right? So that's a big if and proportional. It's a big if and it's a big might or maybe. But let's understand the might first. Why would this be good? So what I'm going to do is I'm going to first start out with what's called a full binary tree. Right? So this is a full binary tree. And let's observe the depth at each level and the number of nodes at that level. When I say full, I mean that every node except for the last level will have all the children available. So in other words, the first root here is going to have both of its children. It's not going to have just a left or a right or nobody. It's going to have both of its children. Remember that the depth here is 0, the depth here is 1. At the next depth, at depth 2, we have 4 more children. So the number of nodes at each depth is going to be 1, 2, 4. If this one has every single child, at depth 3, how many nodes are we going to have? 8. Do you start to see a pattern here? At depth k, I'm not going to draw it, but at depth k, how many nodes are we going to have at that level? At that level? 2 to the k. All right? So it follows a geometric progression here. Powers of 2. 2, 4, 8, 16, 32, dot, 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 2 to the k. Why? Because it's binary, right? You're going up by 2. You're doubling it each time. Now, if I said that you had depth d, right? How many nodes are going to be at that depth? Well, same thing here, 2d. But what is the grand total? Grand total. All right. Add all of these up. Add up 2 to the 0 plus 2 to the first plus 2 to the second plus 2 to the fourth plus dot, dot, dot plus 2 to the d. There is a nice series, right? Give myself some more room here. Going from k being 0 up to d of 2 to the k. All right? This is why I used k instead of d. This is going to start at 0, 1, 2, 3, 4, all the way up to d. 0, 1, 2, oops. Duh. 3. I was thinking something else there. All right. 4, 5, dot, 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 all the way up to d. Can anybody tell me what the closed form solution of this is going to be? You didn't memorize the series in, say, calculus? No? Here's the general form. I running from 0 up to, say, n of x to the I. This is going to be x raised to the power n plus 1 minus 1 all over x minus 1. Our x, however, like good computer scientists, is always going to be 2, binary, right? Base 2. So when we replace x here with 2, what happens to the denominator? Or, the denominator. 2 minus 1 becomes 1, goes away. And we're left with 2 to the n plus 1 minus 1. So this is d, 2 to the d plus 1 minus 1. Okay? That's n. N is the number of nodes in a full binary tree of depth d. Flip that around. Right? This is the depth. If I asked you what the depth of a tree is where you've got n nodes of a full binary tree, that means I want you to solve for d. So let's go ahead and repeat it over here. 2 to the d plus 1 minus 1. Okay? How do I get rid of that minus 1? I just add it to the other side. 2 to the d plus 1. How do I get rid of that 2? Logarithms. Base 2, but we're all good computer scientists, so don't even bother writing it. There we go, move it in. That gives us d plus 1. What do I do with that plus 1? Take it to the other side, and I have that d is equal to log base 2 implicit of n plus 1 minus 1. Now, in the grand scheme of things, we've already seen big O analysis. Is that plus 1 minus 1 important? Nope. This is order log n. In other words, if we can make all operations proportional to the depth, and we have this guarantee that the depth is going to be logarithmic, then we've got what we want. Right? So if we can make all operations proportional to d, and d is going to be order log n, Good. Then we have efficient operations for all operations. Right. And we've achieved our goal. It's not as good in some cases. For example, with a linked list or with an array-based list, there's always going to be some operation that is constant time. You pay for that with this much more horrible linear time operation. But with a binary tree, if you can make everything logarithmic, yeah, fine. You're not going to get that constant time behavior on some of these operations, but you're not paying big time for other operations. You're paying much less for everything, right? And that's going to be much, much better. Now, do we have a guarantee of this? Well, let me draw you another tree here. 10, 20, 30, 40, ... 100. There are 10 nodes in here. What's its depth? Be careful. Remember, if I've got 5 fingers, how many gaps are between the fingers? 4. So if I've got 10 nodes, how many edges are between those 10 nodes? 9. In other words, the depth here is order n. What did I just draw here? A linked list, right? Where you've got such that everything only has one child. Right? So a binary tree offers a little bit more structure, okay? Now, where have we seen this log n before? What kind of what algorithm gives us efficiency of log n? Binary search. What's the relationship here between binary search and binary trees? Think about your array. In order to do binary search, what do you need to do? It needs to be sorted, right? So everything over here is less than m. Everything over here is greater than m. Why? Because binary search, you jump to the middle. If that's the thing that you're looking for, great, you're done. Otherwise, you go left and you go right, or you go right. In other words, you cut it in half each and every single time. N divided by 2, divided by 2, divided by 2, divided by 2. That's what gives you that log behavior. What is the relationship between that and a binary tree? Well, instead of having this guy in the middle of an array, let me go ahead and expand it so that it is a single node that has a left child and a right child. And I put everything in that array on the left child over here, less than m. Put everything over here, greater than m. Right? Now can you see how you can kind of simulate binary search? If you start at the root here, and the thing that you're searching for is m, you're done. But if the thing that you're searching for is less, you can go this direction, and you don't even have to worry about this direction. You effectively cut the tree in half each and every single time you make a comparison. For that, however, we need a little bit more structure, and that's a binary search tree. Okay. With our remaining time here, let's get started on an implementation. And to start, I'm going to go ahead and create a node, a binary tree node. I'm immediately going to parameterize it because it's going to be holding data. Private, final, whatever, element, T of type T element. Or just call it what it is, data. I'm going to get rid of that final there so that it actually compiles. Right? If this were a linked list, what would it look like? We would have a node of the same type that would be next. We don't have just next, right? What do we have? We have a left child and a right child. So let's go ahead and replace this with left child and right child. It's probably also going to be convenient to go back and forth. Right? I showed you a linked list that only went one way, and then I mentioned that there is a doubly linked list that you can go back the other way. What does that look like with respect to a tree? At a node, you can go to left or you can go right. How would you backtrack? What is that guy above us called? If this is children, right? I've got my children. This person up here is my parent, right? Parent. Right? There we go. Have you ever heard this riddle? So here's a mirror, or no, sorry, it's a portrait, right? So there's this portrait, and there's this person in this portrait, and this person walks up to it and says, "Oh, I recognize this person. Brothers and sisters, I have none, but this man's father is my father's son." Who's in the portrait? So, parent, child, brothers and sisters, I have none. So no children, no other children. They're a single child, right? But this man's father is my father's son. Who does he recognize in the portrait? Himself, right? That's why I screwed up at the beginning. I said it was a mirror, right? It's not a mirror, it's a portrait. Otherwise a mirror would give it away right away, right? So there is a nice parent-child relationship, right? I forget where that's from, right? Or it might just be, general culture or whatever. All right, so there we go. Let's go ahead and actually create that binary tree. I'm going to, again, parameterize it so that it can hold any type. What would you put in this binary tree? Would you put a list of binary tree nodes? If you do, you're basically keeping track of every single node, right? That doesn't sound like a tree to me. What does that sound like to you? Sounds exactly what it is, a list. An array-based list, say, or a linked list. That's not what we have. What do we have? Binary tree node. We only keep track of one node because all operations are going to start there at the root. Just like a linked list, you only keep track of the head and or the tail if you really want to, right? But you're keeping track of one node. Anytime you added a node in a linked list or removed a node in a linked list, what would be there? Or what would you do? Keep track of the size? And you would initialize both of these things in a constructor. Public binary tree. Yeah, there we go. Nothing. This dot size is equal to 0. This dot root is equal to null. There. There's our empty tree. Right? By the way, what's the... if I just had a regular old tree here with only one thing in it, what's the depth of that root? What was it again by convention? 0. And so, therefore, the depth of the tree is going to be 0. What's the depth of this tree right here? Careful. You don't even have a root yet. So your tree looks like this. There's nothing there. The depth, there are no nodes. So the depth of the tree, by convention, what we're going to do to make everything work out is that it's going to have -1, the depth of that tree. All right? Remind me of that when we come back to compute that kind of stuff here. Don't have a way of putting stuff in yet, do we? So let's go ahead and add a method to do that. Public void add as new root. There we go. Element here of type T, X. Does that sound right to you? Always add it as a new root. Okay. When we did our linked list, we did have a method called add new root, or add new head, or add new tail, or something like that, right? But that was for demonstration purposes. This is going to be a collection that holds stuff. We're going to put stuff in, we're going to take stuff out, we're going to search for stuff, et cetera, et cetera. Do you want to have to be worrying that it's a tree every single time you interact with it? No, you just want it's something that holds something. Just like a list. Do you want to have to worry that it's a linked list or that it's an array-based list? No. You just want to put stuff in. That's its business. If we did something like this, it would be called a leaky abstraction. We're forcing the outside world to deal with it on its terms, rather than the outside world just put stuff in, put stuff in, put stuff in. In other words, insert that element. That's a much better abstraction. Do we have to worry that we're inserting it as a leaf, as a node, somewhere in between, right? I don't care. I just want to put stuff in and take stuff out. This is the correct abstraction. And I'm mentioning that here and with only 2 minutes left because as you start designing your sorted list data structure, think about it. What if I did this? Public void insert at index, tx int index. All right. Well, first of all, in the context of a binary tree, does it make sense to talk about indices? Not really. What if you did this with your sorted list? Here's my list now. It's sorted. It's 10, 20, 30, and 40. I want to insert 42. Should I be allowed to insert this just any old location? Go ahead and insert it right here at index 0. Go ahead and insert it here at index 2. Does that look like a sorted list to you? Doesn't look like a sorted list to me. In other words, should you have a method like this in your class? Certainly not a public one. Right? If you made it private, okay, yeah, that's perfectly fine. Right? But a public method, that doesn't look like a sorted list to me. Right? Okay, keep that in mind as you are designing your sorted list ADT. It can be a linked list, it can be an array-based list. That's what we're expecting. If you want to look ahead and make it into a binary search tree-based list, go ahead and do that. Right? But whatever you're going to do, make sure that it's a correct implementation, that it's a correct interface, that it's not a leaky abstraction. All right, we'll pick it up there on Wednesday.